All right. So far in Chapter 5, we've looked at scatter plots and linear regression. This next section is on nonlinear regression. And this is what we would use if the data had any sort of curvature to it. So if this is my data, this fits very nicely with a straight line, and I would use a linear regression model with that, and everything would be nice. If I had other type of data with any sort of different type of movement to it, then I might want to switch to a nonlinear type of regression. So for instance, if this is what my data looks like, no straight line is going to fit that very well. But if I use a quadratic equation or a parabola, that will fit nicely. So and this is just my usual quadratic equation format. I just got an x squared in there now. There are also logarithmic types of regression. So if my data rises quickly and then starts slowing down, I could use a logarithmic equation for that. I could also use a square root type of regression for that. So here I could use the natural log of x or log base 10 of x. Associated with that, I've also got an exponential type of regression. So if my equation's shooting up very quickly, here we wouldn't put the exponential on the x. Instead, we'd put the y value inside of a logarithm, and essentially that's the same thing. And then there's basically any of our basic equations, we can fit a type of regression with that. So linear regression will still work with these, it just won't work well. And so if I've got something like this, and I try to use linear regression on that, I'll still get my best fit line, and who knows what it will look like. My R value will be close to 0. Because there's not that nice linear correlation between the two variables. Even though my R value is close to 0, though, it doesn't mean that there's just no association there. It just means that the association isn't linear. So when you see that R value in a paper, be a little bit careful about that. Also, if my R value is close to -1 or 1, that means there is a linear association, but there might be a quadratic association or one of these other nonlinear regression types that will best fit that data. So if the R value is close to -1 or 1, linear will work well, but there still might be something that works better. All right. 5.5 is on logistic regression. I would skip this, but I get the feeling that this comes up in a lot of medical journals and pharmacy-related applications. So I'm just briefly going to go over this. Logistic regression we use for variables that has some sort of probability of success, or anything that's binary, a variable that's binary, so anything that's a yes or no, or success or failure, or anything like that. So that would be my y variable. My x variable would still be some quantitative value. So my example of that kind of looks like this. My x variable has different values associated with it. My y, or here we call it the p for probability, is either a 0 or 1. And basically, this is useful when I've got data that looks like this. So for the low x values, we tend to get zeros. For the higher x values, we tend to get ones. And the model we end up using for something like this is what's called a logistic curve. And our p-value there is given by this formula. And to get that formula, to find those values for A and B, those are still our constants in that. We use the linear regression process that we already know. With those p's and our x value. So we use this, we take our p values, we plug them into that, and then we use whatever x values we have. So if you're interested in that, that's section 5.5. There's a lot more details and examples in the book. Uh, 5.6 is another section on communicating results and interpreting results that other people have given with regards to this bivariate data where you've got scatter plots and that sort of thing. When we're looking at a scientific paper on these things, one thing we want to do is make sure everything's been properly reported, and again, make sure the appropriate measurements have been used. For instance, look at those R values and the R squared values. And make sure that the regression kind of fits what the data looks like and that sort of thing. Another thing about communication is that models are good for getting an idea of what's going to happen with other tests that we can do, what will happen in the future basically, but we don't want to extrapolate too far. We don't want to base too much on a model. So what I mean by that is, let's say I've got some data and I fit that with a linear regression model. If I have another x value and I want to figure out what y value to expect, I would plug in the x, crunch through, and get my y value. If my x is sort of in the middle of the rest of the data, then that'll work okay. I'll just go up and get the corresponding y value, and that'll be a decent estimate. We want to be very careful, though, when we're going outside of the range of the data we've already got. So if my x value is over way to the right, then I'm taking this point on my model and getting that y value. Since we don't have any data in that range, we can't be certain that the model will continue to be linear. Maybe after a while, when my x values get high enough, the model will start looking more exponential or logistic or something like that. So be careful about extrapolation, essentially. The last thing is about correlation. Just because two variables are related to each other, just because we have this relationship between two variables, that doesn't mean that one variable is causing something to happen in the other variable. So this is particularly true if we do an observational study. If you do an observational study and you figure out that my two variables are clearly related to each other, even though it's obvious that one has an effect on the other, we can't specifically say that formally because of due to the data that we've collected. To imply causation from a study, you have to actually do an experiment. So, and this is a formal statistics idea. The general idea there is with an observational study, there may be other variables that are affecting things. So with an observational study, there may be some third variable that's affecting both your x and your y. With a designed experiment, it's generally accepted that those third variables are being controlled and or they're fixed so that they're not having as much of an effect on anything else. All right, that's good enough. Thank you.